In this lesson, we will consider what happens when an alkyl halide can eliminate to give more than one different elimination product. And that will get us into a discussion of what we call Zaitsev's rule. So as an example, we will start by considering 2-bromobutane. So it can produce two different elimination products upon treatment with base. You can have 2-butene with the double bond between carbons 2 and 3, or you can have 1-butene with the double bond between carbons 1 and 2. Okay, so how does this work? Well, there are two different types of beta hydrogen on 2-bromobutane. And for the purposes of this discussion, I have them labeled type A and type B. So the 3 hydrogens on the terminal carbon are labeled type A, and then the 2 hydrogens on carbon 3 are labeled type B. There is a hydrogen on carbon 2, the carbon that contains the bromine, but remember, that is not a beta hydrogen, so we are not going to be able to remove that in an elimination reaction. It's going to sit there, but it is not labeled A or B. So since A and B are two different types of beta hydrogens, we can consider in turn removal of HB and see how that leads to a product, and then after that we'll consider removal of HA and see how that leads to a product. So in this case, we're going to do this example with the E2 elimination mechanism. I could just as easily derive the same result using the E1 elimination mechanism. So E1 and E2 both give the same products or product mixture. Just in one case you have to kick out the bromine, in the other case you have the carbocation. So in the C2 mechanism, I'm going to have the base first going after HB. So we take a curved arrow from the base to HB. We use the electrons in the carbon-HB bond to form the carbon-carbon double bond between C2 and C3. And then at the same time, we kick out the bromine leaving group, and that leaves us with 2-butene, okay, with a double bond between carbon 2 and carbon 3. If we do the same analysis for the removal of HA, we now have a curved arrow leading from the base to HA. Again, we use the electrons in the carbon-HA bond to form a C1-C2 double bond, and at the same time kick out the bromine as a leaving group. Removal of HA leads to 1-butene. So which product will you get? Well, the way I want to address this first is to ask, what would statistics predict? Well, there are 3 hydrogens of type A in this molecule and 2 hydrogens of type B. So if it's equally likely that you remove a type A hydrogen as it is that you remove a type B hydrogen, we would expect a 3-to-2 mixture of products favoring 1-butene. Well, now we have to introduce Zaitsev's rule. Zaitsev was a Russian chemist who lived a long time ago, and his rule is that elimination will favor the pathway leading to the more substituted alkene, which in this case would be 2-butene rather than 1-butene. And the reason for this is that more substituted alkenes are actually more thermodynamically stable. So if you were to combust them and measure a heat of combustion, you would actually get more energy out because the molecule itself is more thermodynamically stable, starting at a lower energy point. And the difference between a terminal and an internal alkene is about 8 kilojoules per mole. So it's not a ton, but it's still enough to cause some bias into the product formation. So having said this, I need to introduce a slight aside and talk about what I mean by more substituted and less substituted alkenes. So alkenes are classified based on how many of the 4 positions on the alkene carbons have alkyl substituents. Okay, a double bond by definition is between 2 carbons, And if 2 of the bonds are between those 2 carbons, that leaves 2 more positions on each of the carbons, so a total of 4 positions. So in a monosubstituted alkene, which I will also sometimes call a terminal alkene, there is 1 alkyl group and 3 hydrogens occupying those 4 positions. For disubstituted alkenes, there are actually 3 options. So you can have what I call a 1,1 disubstituted alkene, where the 2 alkyl groups are both bound to the same carbon and the other carbon has 2 hydrogens. Or you can have a 1,2 substituted alkene, where each alkene carbon contains 1 alkyl group and 1 hydrogen. In this case, a 1,2 disubstituted, you have to consider cis and trans. So depicted here are the trans 1,2 and the cis 1,2 respectively. If you have 3 alkyl groups on the alkene carbons and only 1 hydrogen, then you have a tri-substituted alkene. And then finally, I think you see where this is going. If you have 4 alkyl groups and no hydrogens, you have a tetrasubstituted alkene. Okay, so let's get back to our example, our 2-bromobutane. So what actually happens in this reaction? Well, Zaitsev's rule would suggest that the major product is 2-butene, and as we already saw, 2-butene is what you get as a result of removing HB. So do you just get 2-butene? Do you get some 1-butene? Do you get more 1-butene? Well, it turns out that this is a little more complicated than it appears at first glance, because what products you get in what ratio actually depends on the size of the base. So hydrogens of type B are more sterically hindered than hydrogens of type A. I did not draw out every hydrogen explicitly for the methyl group on carbon 4, but I think you can see from what I have drawn here that hydrogens A are completely at the edge of the molecule, at the periphery of the molecule. But the hydrogens of type B are closer to the middle of the molecule. So as a result, if a base is just coming in and attacking this molecule, it is more likely to crash into the side of the molecule than it is to crash into the middle of the molecule. So for a small base would be able to get into the middle of the molecule and remove HB to give you the more stable Zaitsev product. However, large bases will encounter too much steric hindrance if they attempt to remove HB. So they're going to take that easy route and remove HA to give more 1-butene. So the internal, the more substituted alkene, we call the Zaitsev product, because that's the product you get from following Zaitsev's rule. And the less substituted alkene, the terminal alkene in this case, is what we call the anti-Zaitsev product, because it is not the product that Zaitsev's rule would predict. So in order to finish this discussion, we have to somehow categorize bases as either small bases or large bases. So the general rule that I go by, and different people may have different definitions of this, is that a large base is T-butoxide or larger. Okay, so if you have a base that's that size, it's going to start to favor the anti-Zaitsev product over the Zaitsev product. And then everything else, common bases such as hydroxide and methoxide, we will count as small bases. We'll see in a subsequent lesson that water is also going to be in this category of being a small base, because we're going to need to use it as a base in certain reactions. So in these cases, where you have a smaller base, you're going to get more of the Zaitsev product. Now, you're never going to get 100 to nothing. One of the problems with elimination reactions on unsymmetrical alkyl halides like this one is that you do get a mixture of alkene products. In this case, you will get a mixture of 1-butene, cis-2-butene, and trans-2-butene, and it's hard to control that mixture. But what Zaitsev's rule is telling you is which will be the major product in that mixture. Okay, so with a small base, it's 2-butene, and with a large base, it would be 1-butene.